see that now. So what I'm writing here, I'm writing the density of the complete data vector. Remember I told you I will put as missing the random effects, individual parameters. So this is the density of the complete data, Y phi. And the density of the complete data, this is joint density. I could write it as the conditional density given phi times the density of phi given the parameter. Now, what's going on? I will have to take the log, I will take -2 the log of this. But you can notice that conditionally to the random effects, what's going on? Conditionally to the random effects, everything becomes independent. So it's a nice thing. If conditionally of the random effects, if you knew the random effects, everything, there is no more correlation. So now it's very easy, all the Yij are becoming independent. So you can easily write the log of this density. -2 will give you n log of sigma squared plus 1 over sigma squared, the sum of ei prime ei. This is just the sum of the square residuals. And this is the density of this part. It's very simple. Now we have the density now of the random effects. There is no difficulty of writing because we have made the assumption of normality. Remember, phi di is beta variant G0. So we'll write the density of the random effect, Phi minus its expectation, transpose the inverse of variance covariance matrix, Phi minus its expectation, plus the log of the determinant of the variance covariance matrix, times the number in unit. So we have already the log of the complete data set. But this log depends on something which is not observed. Which is not observed, this is not observed. And here, it's also there, in the residue. So in fact, this part is not really observed, and this part too. So we have to consider taking predictors of these two parts. So that will be the E step. Oui?
What do you mean with the CST?
Will be constant. No, I forgot about the some of the constant. You know, it should be n log 2 pi and I log 2 pi. No, this 2 pi part. Just the part involving the pi's. But all is complete except the pi's. So it should be here n log 2 pi, and here should be I log 2 pi. I forgot about the pi's. So the E step is to take the conditional expectation of my complete data likelihood given Y and given the current value of a parameter. And in short, I will write this conditional expectation at E conditional at iteration T because it depends on the current value of a parameter. So as I told you, what is not observed is this part and this part. So I have to take the conditional expectation of this part, this sum of the square residual, and this quadratic form. And usually in linear model, we know how to do that. It's very simple. We can do it, we can write it analytically. But here is the trouble. In nonlinear, there is no more analytical expression for this conditional expectation. So what we will do, if we don't know it analytically, we will do it numerically. And this is the basis of the so-called stochastic EM or Monte Carlo EM. At the E step, instead of taking the analytical expression of this conditional expectation, we'll take it numerically. So what we have to do, in fact, we have to evaluate, I will write it generally, we have to evaluate the conditional expectation of this SI, where SI is a function of the random effect. Remember, this is the function of the EI, and this is the function of TI, as EI is YI minus F of TI. So all these terms are functions of TI. So what is the conditional expectation of this function of TI? Is the function of TI times the density of TI given data, given the parameter, integrated out with respect to phi. This is the definition of the conditional expectation. I have to take the expectation of this conventionally to this and this. This is random, and this indicates the condition. So we are back to what we have seen in the first lecture, second lecture on Monday, how to compute integrals. If we don't know how to compute them analytically. So we have seen that if we use, for instance, traditional Monte Carlo integration, if we use importance sampling, if we use Markov chain Monte Carlo, we will do that in picking, in sampling this distribution. So in sampling, we couple the set of realizations, phi1, phi k, phi k, evaluate this function, and take its empirical mean, sum of s of phi k divided by k. So it's very simple. You pick numbers in this distribution, you evaluate the function, and you average it. So there are several ways. We can do it, for instance, with Metropolis Hastings, and it's what is done in monoliths. With proposal, we have seen that. The proposal, we won't sample in that. We will sample in the independent sampler, or we can sample in a random walk. I won't go back. There is a lot of choice the way you sample, because you won't sample directly this. You can do also we'll see later on. We can do with importance sampling, what was being proposed by Walker. Let's go back. If you do it by Metropolis Hastings, what is done in monoliths. In monoliths, they are doing a second step called the stochastic approximated EM. What is the stochastic approximated EM? Is to evaluate this Qi at iteration t, instead of just taking the empirical mean of this S as a function of the sample you draw, you recycle. These people are really efficient. They recycle the previous value of Qi, and they will weight this part with a given coefficient, gamma, and this part by 1 minus gamma. So we will start, for instance, with gamma equal 1. So we'll have only stochastic evaluation of the Q up to a given point, t, given number of iterations. And at this point, you start to recycle. you use your previous value. So you will take, in that case, something less than 1, and that will become positive here. And you can parameterize this gamma as 1 over t minus this point. So you will realize that gamma will decrease from 1 up to something very close to 0, with the weight allocated to this part smaller and smaller. So you are recycling more and more. And this recycling is not some saving, but it's also a way to stabilize and to make the algorithm converging more rapidly. It's kind of smoothing. And we saw that on the graphics. It will smooth the variation. And this is the algorithm proposed by Kuhn and Navien in 2005. So-called stochastic approximated here. So we evaluate the integral by this, and we recycle the previous value from one iteration of the EM to the next. So this is what is used in monoliths. Now, just give you the procedure proposed by Walker. So Walker did not apply metropolis hastings. He was doing important sampling. Remember, we see that on Monday. So what do you do when you are making important sampling? You have to sample in an importance distribution in the proposal, and we choose to sample in the distribution of a random effect. So you multiply by this and you divide by this. Remember, we start from here, you multiply by this and you divide by this. And you will sample directly here. And in that case, you will have to average all this part. This part is the so-called W, the importance weight. But here, this importance weight is very simple. P of phi given yi theta over P of phi given theta. So this is proportional of this density times this one. So what's going on? This will cancel out, these two will cancel out, and we'll get something proportional to this, because this doesn't depend on phi. So this is, what is this? This is very simple. This is the conditional likelihood given the random effects. So we compute this as weights. And remember, you compute the weights and you compute the relative weights. So you take this as weights, and the sum of this, you have the relative weights. So these are the weights and the sum of the weights times S. So it's very simple. You sample in this distribution of random effects. You compute the weight, the relative weight. You multiply by S, the value you have sampled, and you average. Take the sum. This is the so-called importance sampling proposed by Walker. The problem with importance sampling is we need to sample more values than, for instance, in the stochastic approximated EM. You will surprise that in the SAEM, you will sample very few values. You can sample only 10 values, and it works. It's a kind of miracle due to the smoothing part. Now, we are only at the E step. Remember, we are at the E step. So we have to move to the M step. So that means that now we know that this is now a numerical value, because we have evaluated numerically, and all of this is now a numerical value. So now we have to differentiate with respect to the parameter. So we have to differentiate with respect to beta. We have to differentiate with respect to sigma square. And we have to differentiate with respect to the element of G0 to maximize the function. So, for instance, with respect to beta, so what's going on? With respect to beta, we'll have to differentiate this part with respect to beta. This gives you a prime G0 minus 1, conditional expectation of phi I minus this expectation, sum over I from 1 to big I minus 2. With respect to sigma square, we'll have n over sigma square. Differentiate this, 1 over sigma 4 times this. And with respect to G0, it's a bit more complicated because you have to differentiate elements of the matrix and determinant. And this gives you this formula. It's a bit tricky, but it could be handled out very easy. So now we set all these three to 0 and solve it. And we'll get the maximum. And here you will see the solution are very easy. What do we get? Here, the maximum with respect to beta, the fifth iteration. This quantity minus 1. This sum, A prime G0 minus 1, evaluated at equation T. And here, instead of having phi, we have the conditional expectation of phi. Because remember, this was non-observed. Sigma square is very simple. It's the sum of the conditional expectation of the square residuals divided by m. It makes sense. You take the residuals, you square them, you take all the sum, but as you don't observe them, you take their conditional expectation. It's what is very interesting with EM is that the solution always makes sense. You can interpret them very easily as compared to traditional ML, where you have a nasty equation and you don't know why you have this equation. Now here for G0 is also very simple. It's 1 over the number of individual, this conditional expectation. And what's this conditional expectation? Is sums of I, UI prime. So this is square of random effects and co-products of random effects. And that makes sense to evaluate variance-covariance matrix. To take sums as U square and U V square. Notice that this, for the statistician, this represents what we call sufficient statistics. What represents for the variance, this, the square, are a kind of summary for this parameter. And this square and product are also a summary for this. But here, what do we have? We have a GLS system. Remember? We'll take the blackboard, make something on the blackboard. With EM, the solution are always very easy. Imagine, I told you have I equal I beta plus UR. Now forget about all the stuff here, and I give you this. And I want you to give me an estimator of beta, and I tell you I will observe this phi. I'm God, I know phi. So this is a linear model. Y equal x beta plus e. No? It's the same structure. So how you will solve that? You will write the GLS equation. No? So you will get some P prime I. Variance covariance G0 minus 1. Pi beta hat equals sum of R P prime I G0 minus 1 Pi. It's almost what I have here, no? Except that here I assume that Phi was observed, but it's not. So what I'm doing, I'm replacing what is not observed by its conditional expectation. So you realize immediately that that makes sense for the imaginative people. They don't go even in the all the derivation. They can guess that immediately. But you have to be careful because sometimes it's better to check with the derivation. So you see, all this makes much sense. Now, we were animal breeders working with these people in statistics, and we were very unhappy with the name. So we decided to propose something as Raymond. And this has been done by a student, Christian Mézard, Florence, and myself. It will just come out very soon, I think. Maybe it's already on the website, in the Biometrical Journal. So we propose a Raymond estimator of sigma square on G0. And now it's even simpler than ML with the stochastic here. It's the trouble. Raymond becomes more simpler than ML. So now what we do, we'll use the interpretation of Arville in 1974. I told you Arville told us that we can interpret Raymond as the maximum of the marginalized likelihood. So the likelihood being a function not of the fixed effect on the variance parameter, but just of the variance parameter after integrating out the fixed effect and integrating them out with a flat prior on beta. Is it what you were thinking about? Okay. So, if it's a flat prior, it's become a constant. So we have to make this integration. Now this again, the notation, the first step, the second step. And so the trick, where is the trick? The trick is to integrate this beta. It's not obvious to make integration, we have seen that. So there is a trick. And the trick is very simple. You put the beta among the missing part. So remember before the missing part, the y and the random effects. Now put also the fixed effect in the missing part. So the parameter vector becomes only the residual and the variance covariance G0. And if you put it as a missing part, remember it's missing. So you will have to eliminate it in taking some conditional expectation. So you integrate this beta automatically by the EM process. So it's the magic of the story. You put it in the missing part and it's automatically integrated out. And so I won't enter in detail. The equations are exactly the same. So I won't do all the derivation. We got exactly the same part here. And here we have to give something for the fixed effects, because in fact people want estimates of fixed effects. So what we suggested is to take the conditional expectation of the fixed effect given the data. You have to make some correction here, given the data and given the variance equal to their Raymond estimate. And this is very easy to do because you don't have to compute that. Because as you are sampling, we'll apply a Gibbs sampling. We do it by Gibbs sampling. So at the end of the story, we have this. we have a lot of values of this. So we just have to average these values. So you know, it's very, very easy. And we have seen, you will see that on the paper, but we can remove a large amount of bias with respect to the ML estimation of G0. Because sigma squared is like in mixed model, linear mixed model. There is not so much bias as long as you have enough observation. But here, maybe some large bias. So we can do ML, also we can do Raymond. It's not yet implemented in monoliths. Because surprisingly, it seems that the statisticians, some of them don't know Raymond, or those who know them don't see really the interest of Raymond. So very funny. Now last, but not least,